Here's an explanation of experiment 15, freezing point depression. So here we're looking at colligative properties of different substances and how much their freezing point is changed based on different factors. So here in the lab manual, lots of equations are written out for you for part A, part B, and part C. I'll go down here and run through the data page. So you are given all of this data that you'll use to then calculate all of the missing boxes. So for part A, what you're actually looking for is the whole point is to solve for the Kf value of ethylene glycol. So what we know here is that K little f is equal to delta Tf, so the change in the freezing point, over little I, the von Hoff factor, times molality. So here, using the given data, we can find all of these different variables. So for delta Tf, what we want to know is that typically water freezes at 0 degrees, but in the data, you'll be given the final freezing point. And what you'll be able to do is subtract those two to figure out what the delta Tf is. How much did the freezing point change? Little I is the von Hoff factor. Ethylene glycol is molecular. It's all nonmetals. So I is going to be a value of 1 here. It does not break into ions. And then molality, if you remember, molality is always moles solute over kilograms of solvent. And if we look at those two things, we're going to know our moles of solute, which is right here, and we're going to know our kilogram of solvent, which is right here. So we'll be able to do moles over kilograms to get our molality. And then we have everything we need. We have our change in freezing point, we have our little I, and we have molality. And you'll just do that for all three trials here. Part B, what you're looking for instead, is you are going to solve for an I value. We can always predict an I value, so given a formula. For example, NaCl, it's ionic, so it should break into ions, 1 sodium and 1 chlorine. So our theoretical I should be 2. But experimentally, we'll be able to calculate and see what our I value actually comes out to be, which we can rearrange our equation for little I equals delta Tf over little Kf times molality. So here, if we see where we're getting these variables from, again, water generally by itself will freeze at 0 degrees. And here we will be given a final freezing point again, so we can subtract and figure out the difference there. That'll give you your delta Tf. Your Kf is coming from part A. So you'll come up here, and whatever Kf value you found and your average, that's what you'll bring down for your Kf. And then you just have molality to find. Once again, molality is moles of solute over kilograms of water or of solvent. So you can use these two to calculate your molality. Then you know all three values. You can plug them in and find I, and you'll do that for each of these three trials. And then lastly, for part C, you're finding molecular weight here. So molecular weight, experimentally, what we can do is use this equation, which is given in your lab book, but molecular mass or molecular weight is going to be little I times Kf times your grams of solute over delta Tf times your kilograms of solvent. So you'll be given data up here that you can end up working with to find each of these. So little I, we'll go ahead and say that urea is a molecular compound. So what that means for us is that I is equal to 1 again. So we already know that. Kf we already know from part A of the experiment. So you're just bringing that down again. Grams of solute, here's going to be your grams of solute because that's your urea. So grams solute. And then delta TF, again, water should freeze at 0, but you'll be given a final freezing point. So here is going to be your delta TF once you subtract the two. And then kilograms of solvent is right here is your kilograms of water. That is your kilograms of solvent. So you can plug all of these values in to come up with your molecular mass. Then you'll complete the post-lab questions using those same principles and calculations.